So as we continue in chapter 4, the last third of the chapter looks at models that we use to understand the electrons. So we know from previous models we have the protons and neutrons in a nucleus. We know that the protons give the identity, but it's the electrons that have to do with the chemical reactivity and the bonding. And so the previous models did not allow us to predict or understand why two elements might bond, for example. And so we're going to investigate how we can understand the electrons to help us with bonding in particular. So in this video, we're going to work on the numbers 8 and 9 here in your chapter. Now, I included this illustration I have in previous videos as well, just to kind of give us context for this evolution. And so we had Dalton in the 1800s, and then we get J.J. Thomson and Rutherford, which are really bringing us to the nuclear model. And remember, Rutherford, when we think about the nuclear model, initially, we just think of the electrons as being outside the nucleus. Well, now we're going to start to think, okay, how can we think of that a little more specifically? So we're going to look at Bohr's model first, and then in the next video, we'll look at the quantum mechanical model, which is attributed to Schrodinger. Before we get into Bohr's model, we need to know some properties of waves, just because we need to take a look at his experiments, which are super cool and understandable. Now, all of this involves math, not overly complicated math, but for our introductory course, we won't be doing the mathematics behind these models. If you are planning to, and I hope you are, to take the next level chemistry, then when you will go over these models again, and at that point you'll start using the calculations, so you'll have some numbers that are associated with these different properties. So the properties of a wave that we would pay attention to are its wavelength. And the symbol behind it, this is a lambda, and that's just the symbol they use for wavelength. And wavelength is measured as either from a peak of one wave to the peak of the next wave, or it can also be measured equally from the trough or the lower part of one wave to the trough of the next wave. And so the wavelength is this distance here. So peak to peak or trough to trough. So that's wavelength. And the wavelength is related. These are all connected to each other. We have the frequency, and this is the Greek letter nu. And frequency is just the number of times that a wave passes a specific point. And then the speed, and for light, the speed is constant. It's the speed of light, and it's 3.0 times 10 to the 8th. And so we have wavelength, frequency, and speed, all which are connected by mathematical equations. I can write the equations here. Again, you don't have to use it, but like if you take the wavelength and multiply it by the frequency, you get the speed of light. So the only reason I'm showing you this is because we're not using it now, but I don't want you to be intimidated when I say there's math. We also know that the energy, which I'm going to be talking about energy in just a little bit, the energy of these waves is, if you take a constant, so that's always the same number, times the speed of light, and you divide it by the wavelength, you can get the energy. So what we can see here is energy and wavelength are inversely related. And we're going to get a visual of this as well. So again, I'm not giving you these equations. You don't have to write them down. Just when I say math, I don't want you to think, oh my goodness, this is the kind of equation that this particular topic has. Okay, so you could do that. Now, here's just an example from your book about wavelength and frequency and how they're connected. So if this energy has longer wavelength, this light has longer wavelength, then it's going to have a lower frequency. And if it has a shorter wavelength, it's going to have a higher frequency. This is also connected to energy, so I'm going to write that next to it. Oh, no, you see it right here. So when you have low energy light, it has a long wavelength and a low frequency. Okay. High energy light has a short wavelength and a high frequency. So what I need you to remember really we're going to start looking, and what I want you to take from this is that if you have low energy, you're going to have long wavelength, and vice versa. If you have high energy, you're going to have short wavelength. And low energy also goes with low frequency, like you can keep that. But the energy and the wavelength is what I want you to keep in mind now, because we're going to look at some illustrations of the experiment and what he saw, and I want to see how it connects, like how Bohr connected. Now, Bohr was a Danish, I think, physicist. These were some mathematical models that he created based on experimentation. So let's take a look. So when we talk about light, and we're really going to be looking at visible light in these experiments because our eyes can detect visible light, but there are also instrumentation that can detect other forms of energy or light. So experiments could be done not just with visible light, but what we're going to look at is through our eyes with visible light. So this energy spectrum is continuous, and when they talk about it here, it's called electromagnetic radiation, and these are just some of the types of energy that are within that spectrum. So there's cosmic rays, gamma rays, X-rays, ultraviolet light are visible, which is here in the middle. It's just a teeny tiny little bit of it. Infrared light, microwaves, TV waves, radio waves. So all of these are a part of the radiant energy spectrum, or what we call the electromagnetic spectrum. And it's just a continuous. It moves from one thing to the other. Now let's connect it again back to what we were talking about. And then I want to look on this particular slide at the visible spectrum. So what you notice is on this side of the spectrum, the cosmic rays, these have the shortest wavelengths and the highest energy. And as you move in this spectrum, we get down here where you have long wavelengths and lower energy. And on the whole spectrum, this is radio waves on this end. Now let's apply this to the visible light, which they have the little box, but then they put the colors below. So we see down here, this is short wavelengths, which means in visible terms, this has higher energy. So the blue light has higher energy and shorter wavelengths. If you go all the way through, here down on this side, we have longer wavelengths. Not the longest, right? It goes to radio. We're just looking at a teeny tiny bit. And this then has lower energy. So notice as you go through the visible part, the different colors are related to different wavelengths, which then can also be related to different energies. Now, I don't know if to remember the colors of the spectra, you might have learned this in elementary school, but maybe not. I always think of the name, it's a pretend name, Roy G. Biv. This tells you the colors of the visible spectrum in the order that they occur. It's red, orange, yellow, green, blue, indigo, which is kind of a blue-purple, indigo, and then violet. And so this is not written, this is written the other way. So this down here, this is the long wavelength with the lower energy. And this side would be higher wavelengths in terms of the visible light and shorter wavelengths. I was thinking higher energy. Sorry. Okay, shorter. wavelength, high energy. Okay, so what I want you to take away from this is we have this electromagnetic or this radiant energy spectrum that includes all these forms of energy which travel through space in waves. Okay, that's how this energy travels. It travels through space in waves. And depending on the wavelength, the energy depends on the wavelengths. And so within the visible spectrum even, there's different energies of light depending on the wavelengths. So I want to just take that idea and let's look at the experiment that Bohr was explaining. So white light, like we might see from the sun, actually contains a lot of different colors, and we call it a continuous spectrum. So here's an example of what happens when we separate the colors, and nature does this for us when we have rainbows. Right? But you can also do this with a crystal and the sun, or this is in lab we use what we call a prism, which is a crystal, but it's designed specifically for this. So here we have this light, and this is white light. This is a continuous light. It has all the colors. They run that light through a thin slit, so they just get a little piece of the light. And they place it through a prism. Now what happens is the different wavelengths and energy, they travel through the prism differently. So they move and bend as they go through the prism. So because they have different wavelengths, different frequencies, because each individual light is different, it travels through the prism differently. And as it travels, then it separates. And so what we would see on the detector is not just the white light, but what we see is up here, and we see the color separating. And if you take physics or if you take the next chemistry, you will probably have an opportunity to look at this firsthand and discuss what's really happening to the light. What we need to know is that not all light travels through a prism the same, and so as it travels and refracts and moves through that prism, we get these separate pieces of color, like it separates out into this really nice rainbow. So this is just white light. This is something that includes everything. All right. So what happened with Bohr is they weren't just looking at white light. He was looking at the light emitted from specific elements in a gas phase. So what he determined, and then we're going to look at the experiment. We're going to go back, but this is what Bohr came up with. So he thought that the energy of the electrons is what we call quantized. Now the word quantized means that the energy had specific values, and it wasn't continuous. The electron did not have any possible energy, but instead had very specific energy values that were allowed. And so what he proposed is you have the nucleus, and that the electrons would orbit at certain energy values around that nucleus. Now they couldn't go in between the orbits. They could only go on a specific orbit. And each orbit had its own specific energy value. Okay, so this was his model. You still had a nucleus, and the electrons could orbit at certain values around that nucleus. Now let's go back and see, okay, what did the experiment tell us? So let's look, like, how did this idea relate to the experiment that he was seeing? So we know that, and we're talking about visible light. We know it travels through space in waves. We know there's different wavelengths, which then indicate different energies. We know if we put white light through a prism that it will separate into all the different wavelengths, into the different colors, into this continuous rainbow that you have. So we know that. But what Bohr saw is he had, in this case, he was studying hydrogen. And hydrogen was the easiest one to study because it only had one electron that would be moving up and down. And so just like a neon light, there was in a tube hydrogen gas, not neon gas. And if you think of a neon light, if you don't put any electricity in, it turns off. But if you put electricity in, then it glows. And this was glowing. So he turned it on. He took the light then, just like in the previous one, it goes through a slit into a prism, and it would separate into colors. Now, these are the three colors that are seen. These are called lines. This is called an emission line spectrum. And I'll describe a little bit more just in the next thing, just to tell you what's kind of happening. So what he noticed is when he separated the colors, for example, in hydrogen, you didn't see a continuous spectrum. You saw very specific colors. Now remember, the colors are related to wavelengths, and the wavelengths are related to energy. So another way to say it is he was observing electrons that were in very specific energies. Now let me take a step back, because you might be thinking, well, how did he know it was electrons? Well, I'm going to draw some lines here. And these lines are going to be like energies. And so what happens is when your lamp is off, it has an electron, and I'm only going to do just one electron here. This is my little electron. I'm just drawing it like an arrow. And the energy is off. Like the light is off. It's just sitting at what we call a ground state. It's at a low, relaxed state. Like it's just sitting there. But what happens is when you turn the light on, you put electricity. You can also use just fire or flame. But we put electricity, we put some energy into that little electron. And when you put the energy into electrons, they don't stay where they are. They go up. So this electron, it could go up to any one of the lines. So let's say it went up to this line. So what happened is the electron is what we call excited. So when you put energy through electricity or flame into a gas, those electrons are going to get excited, and they're jumping up into an energy level. And there are machines that can detect the jumping up. But what this is detecting is the falling down. So electrons don't like to be excited, it turns out. Electrons like being in the bottom. They like being in the ground state. So then what happens is the electron goes back down, and it has energy out. Okay, so the electron relaxes back down, and when it does, energy comes out, and I can't draw it, but this is what my eye is seeing. There's my eye. And I'm looking at this energy, the colors. So see, what Bohr was thinking is, well, my electron isn't just going everywhere. My electron is only going certain places. And how do I know that? Because only certain energies, only certain colors are coming back out. So then Bohr concluded that there are very specific energies that the electron can go to. It can't go everywhere. How do I know? Because it only gets in hydrogen, red, blue, green, and violet. It didn't give me all the colors. So it can't go to every possible energy. The values are quantized. So this is in his model. And so what they've drawn here are little orbits. They didn't draw the whole way around, and you notice they number them 1, 2, 3, 4, 5, 6. And then mathematically, he wrote an equation that would let you, if you put in the numbers, let you calculate this color, like these energies. So he was able to calculate like what energy from his model would give you red, or what would give you blue-green, or what would give you violet. And the electron couldn't go everywhere. It couldn't just go into the middle. It had to go to one of those orbits. That's why it's called quantized energy. So in the Bohr model, or what we call the orbital model, you have the nucleus surrounded by an electron that orbits in specific levels. Now, what we're going to learn in the next video is the electron doesn't orbit. It still has specific levels. So it's quantized. That is true, but it doesn't orbit. So the Bohr model worked really, really, really well for hydrogen. It was beautiful for hydrogen. And they still do the calculations of his model. You can calculate using his equations for hydrogen. But hydrogen only has one electron. And once you started adding in more electrons, the model was not as good. So we'll see in the next video. This is where things like quantum mechanics have to come in, which involve more math, which I can't write just the little equation for, but it involves more math. We aren't doing the math, we're thinking conceptually. So Bohr actually won a Nobel Prize for his contribution, even though in the end it wasn't the model didn't pan out completely. But I always think this is a really good example, because here's a place where the answer wasn't the exact right answer, but the contribution was so great, Bohr gets acknowledged for the idea of having these quantized energy levels. This last slide, and you don't have to memorize any of these numbers, the last slide is just the spectrum of different gases. So these different gases, they're not all the same as hydrogen. They have their own unique fingerprints, and these emission spectra, when you look at what the gas emits, how it relaxes back down in the emission, you get fingerprints of different gases. So it's one way to identify what gas a substance is. For example, even in outer space or something like that, you can look at its emission spectra. So on the top is the continuous one. That's just the white light. But then you'll notice there's other gases, not just hydrogen, helium, lithium, sodium, mercury, and you can see how they vary. So this is a way that gases can be identified. So in the next video, I'm going to do my very best to pick the fruit of the quantum mechanical model so that we have enough information to think about how electrons are involved in bonding.